Yo, hello everyone. So, today I'm sharing another, like prototype circuit that I thought, could like interest a handful of people. This is still kind of experimental, but yeah, just let me show you. So, let me turn it on. Alright, you can see the light bulbs turning on. And I can regulate the brightness here. Alright, before you click off the video, because you think, oh great, it's another overcomplicated light bulb dimmer. I mean, yeah, it kind of is, but uses, I guess, a few interesting principles. First of all, it's like, as you can see, it's just connected to mains, and the breadboard is the control circuit, and we have the power going into the control circuit there. So before I show any waveforms and like bore you with stuff, let's just move over to the schematic, because we can't really see much here from the breadboard. You can only see it working. I guess you can hear this. From that alone, you might be able to guess what the control method is. Alright, so this is the circuit here. Let me get my pointer. So I guess what generates the power is this, which is your standard, I guess, electronic transformer, like self-oscillating half bridge. But here it's like controlled a bit differently. Like that's like the whole point of the circuit, which is making a dimmable electronic transformer. That was the idea. I was gonna use it for a pre-regulated linear power supply, but I can explain why that wouldn't like really work well. And I want to make this video before I disassemble the schematic, because I guess it's kind of interesting, but I don't really need it because it kind of doesn't work for what I need it to work. Maybe I can, there's like some solutions for it. I might keep experimenting, but I need the workspace for something else. So I guess let's begin. So yes, we have the good old legendary, always faithful NE555 PWM here. We have some resistors here which limit the range, so it doesn't like fully go from 100% to 0%. This is your classic PWM configuration: 4-8, 1 to ground, 6 to connected, capacitor, thing. 3 is the output. Same old, good old. Alright, so then we have a Schmidt trigger, I see, the 74HCT14, which is configured in a downward slope detector circuit here. I guess a downward slope trigger. That's what it does. So it's this capacitor resistor configuration here. This makes like the slope. Then we have one trigger. Then we have another, which just inverts the signal. And then we get our slope pulses out here, which then get connected into this transistor. And we also have this transistor, which then connect directly to the output from the NE555. So why do we even need this complicated thing? I mean, it's not really complicated, but whatever. So just imagine this coil here is connected here. So what this does basically is we have a trigger circuit, which is this transistor, which pulls actually the charge of this capacitor. It dumps the charge of this capacitor into the coil. It pulls it like it connects in. It completes the circuit. You can see this is like the output waveform. You have these upper spikes, which are from the slope detector. These are generated by this transistor, which are basically just really small trigger pulses that push the coil high. And then the other transistor is just to short the coil with like low impulses from the, I guess, longer impulses from the NE555. You can see how this looks here. You have the transistor pulls it low, and afterwards when it goes high again, it like pulls it high, the coil, and then it pulls it, then it floats, and then it pulls it low again, and then after that it pulls it high for a short duration. And this we need basically to control this self-oscillating half bridge, which I guess it's like, yeah, it is self-oscillating. That's like what it does. So basically, if it pulls this coil, I can show you that later on the breadboard. If imagine if this is not connected, like, don't think about the schematic now. So we have this, just this. We have this bridge rectifier. We have your rectified mains, which gets smoothed by the smoothing capacitor. You have your 375 volts, positive, negative here. You have these transistors where it's basically the circuit connected here. So what happens? You turn it on, nothing happens. So then you pulse this coil, you give it a voltage impulse. It actually doesn't really matter which direction you give it, but just pulls it and the circuit just starts. It starts self-oscillating and it illuminates the light bulb and it runs at full power. That's basically what this does. But then the interesting thing is, if you short this coil, then it turns off, because then the self-bias from this coil here gets shorted and then it can't drive its own bases, and then the circuit basically dies. So then it doesn't illuminate and that's it. Because you can't really control the duty cycle of this self-oscillating half bridge. So basically the control method I'm using is just PWM. You turn it off, on, off, on, off, on, you know, basic stuff like a motor or whatever PWM control you use. So yeah, you have these are the half bridge capacitors. This is all standard stuff if you know this circuit. Alright, let's go over to the actual build here again, so you can see what the hell is going on here. So now some of these parts should be familiar to you. We have the potentiometer. Actually, let me get my pointer. You have the regulator. This is the base coil, which we saw. This is the self-oscillating winding. This is base winding number 1, base winding number 2. This is the control winding. This is the 330 nano. Here are the two transistors. There's the Schmidt trigger. There's the NE555, and these are the half bridge capacitors. Smoother bridge rectifier. He comes in. The mains come through here, which basically comes through here. These are my protection light bulbs. So if something catastrophic happens, I don't short out the mains. All right. Let me turn on the oscilloscope now. We can look at some of the waveforms and actually see this running in practice. Let me turn this on. You can see the light bulbs go. And here we are. Let me trigger this. Make this time base shorter. And you can see how this looks. So basically, stop it. There we go. I have one of the oscilloscope probes at the output here. From this, you can see this, the trigger impulses from the slope detector. And I have the output on here. This second channel is across the light bulbs at the output, so you can see how the oscillation looks. So you can see it here. This is like low power now. You can see that the half bridge isn't running a lot of the time. It's mostly off. That's how PWM works. And if I control this, you can see how the half bridge stays on longer and longer and longer. Basically all the way that it looks like mirrored. Now the off time is about what the on time was before. And now the light bulbs are bright. And yeah, you know, PWM stuff. And if I zoom in here, you can see how if this wants to trigger, switch to the second channel maybe. It's because it's like mains modulated. It's hard. It's kind of hard to trigger. Maybe if I make this a little bit bigger. I guess it's triggered now, but you can see it's wiggling a lot because it's mains modulated 50 Hertz, so the oscilloscope doesn't really like that. Alright, there we go. That's better. You can see the half bridge switching here. You can see there's like some crossover stuff from the transistors, but it's pretty clean, I'd say. Make this like smaller again, so it doesn't take up all the screen. And yeah, down here, This is the upper thing. These are the trigger impulses. You can see every time it triggers, you can see how the half bridge starts oscillating and then it doesn't. If I switch this to the output of the NE555, you can see that it stays off while the NE555 stays on, which is controlled by the duty cycle, which you can see is basically what I explained on the schematic. And you could say, well, this actually looks pretty decent. And I'd say, yeah, it is a pretty good proof of concept. This has a few flaws, so that's why it's like not really usable in a normal sense, I'd say. So the first flaw is that this regulation is kind of power dependent. So what does that mean? It means that if you load the electronic transformer more and more, there's so much current induced in the control transformer that this circuit stops actually being able to, it stops being able to control the half bridge. It can't turn it off like reliably anymore. So it like stops, you stop having like control over the thing and basically runs away and just wants to run full power. And the other problem is it also doesn't run with no load at all. So if I disconnect this here, leave it for a while, connect it again, bam, it's dead. So I actually don't really know why this happens, because technically the initial impulse, like the impulses I showed you, the trigger impulses, they should be enough to like start the circuit, but apparently not. So if the capacitor fully charges, it just dies. So like need to wait that like this charges, because there's no resistor there. The voltage is just gonna stay on there right here. But you can like self trigger it, which is basically you connect this coil and connect it to the positive here. There we go. Like you touch it, you induce some voltage. There it goes. If I connect the wire again to the control circuit, you can control it again, but yeah. It doesn't self-start up, which is kind of a problem. So initially I wanted to design this to make like an efficient linear power supply that didn't need an iron transformer. Like, you know, the pre-regulated linear power supplies use like SCR regulation for the transformer, which isn't really healthy for the transformer itself. So I guess for the primary, if you use primary regulation, usually you do secondary regulation, but that has its own problems. You need like a big iron inductor as well to like smooth out the SCR regulation, which you need even more weight, which, yeah, I kind of wanted to make a compact linear pre-regulated power supply. And the only problem really of this circuit is the power dependency for the regulation, and that it doesn't work without any like load. I can't really think of any idea to like preload it to always keep it running, but there might be a way to actually keep the electronic transformer always running, because I've seen like some schematics for that. There's like this circuit here is very popular in Russia, so they always do experiments with it. And I think there's like a variation where you add another coupling winding from the output transformer to the base transformer with like a resistor in series, and that like it loads it like kind of right and gives it enough self thingy that it always keeps oscillating. Might have to try that, see if that works and if it's still controllable. Yeah, I guess that's basically it. There is your glorified light bulb dimmer, basically. That's what it is, at least right now. Well, I guess some of you might find this interesting. Here's the schematic again, just for the end. And yes, I might actually have gotten some of these wrong, so take all of this with a grain of salt. The circuit itself is kind of finicky to adjust, so it might not work for you. Let me mention which transistors are these. These are BU2520AF. These are like horizontal output transistors. This is actually a good application for these. Like need a quick, relatively powerful power supply. You can take them out of old CRT televisions and build this. Other transistors work as well, like old ATX power supplies that have like MJ13007 or like generally high voltage transistors, stuff like that. So yeah, I guess that's gonna be it for this like small technical video, and maybe I will post a bit more frequently, but I don't know, I don't really have much to show recently. But yeah, I hope I will see you next time. Later.